Hey, natural science students, welcome back to class. I'm sorry that I couldn't be here today. I am actually attending a funeral in Iowa right now, and I would really appreciate it if you would do what you can to learn this, not so much because it's for me, but because I just want to remind you that you will be tested about what we're learning about Kepler's laws and moon formation next week. So if you pay attention today, the test is going to be easier. If you don't pay attention today, the test is going to be more difficult. I also want to remind you that I have briefed my guest teacher on all of the expectations for class today. So, as per always, the expectation is phones need to be away. And so your guest teacher is going to give you a warning, and if you don't follow the warning, he can take your phone. And I've also instructed him to, write down the names of anybody who's really struggling to focus or not being respectful to people in class, including respect to the guest teacher. And so I would really appreciate it if I didn't have to do any office referrals when I got back. But, I trust you all to make good decisions, and I just want you to feel like you are prepared to show what you've learned about Kepler's laws. Now, the last time we had class, we ended on this idea that there was this guy named Johannes Kepler who's generally credited with observing the motions of planets in the skies and using that information to help him to come up with a set of rules as to how planetary objects, and to be fair, any orbiting object in our solar system moves. And of course, we're just coming off of our study of gravity, so it makes sense that people would start, as they observed how gravity works, would start thinking about how that affects orbiting objects. You've actually seen all these rules in action this last Friday when we modeled planetary orbit in large group. And so it's not like you haven't seen this before. We're just going to more formalize it and nail down what this set of rules are, just like we did with the mystery cube at the start of the year. I also think that it's really important for us to be aware of how the history of science influences how science develops over time. And so in that spirit, one thing that you're going to notice for natural science is that periodically I will do skits that will help you to sort of understand the history. And in this particular case, the history is really, really interesting because this is basically the story of two guys who farmed the workout to two women, and they probably really deserve the credit for this. But there's also crazy things like noses being chopped off and duels and holding your bladder so long that you die from peeing yourself to death internally. So I'm excited to share that with you. And so this is the story of the Keplers and the Brahes, and it's a one-act play, and you can see the cast here. And normally if I was here, I would give you three choices. I would give you the choice to have students read the different roles at their desks. I would give you the choice to come up and act it out in front of other students. But since I'm gone today, I just want to make sure that things go smoothly. So I'm just going to read all the characters, but in amusing voices to try to keep you engaged. And so let's kick it off with the narrator. Johannes Kepler studied at Graz University in Graz, Austria. Oh, the weary life of a math teacher at a university in the late 1500s. After having smallpox when I was small, my vision became weak. You see, my true love is astronomy, and I want to be able to look at the heavens, but I struggle. I'm still very fascinated by the laws that seem to govern aspects of the natural world. I'm not sure what they are, but I think that it is my responsibility to investigate these laws, rather than to just think that what I think must be right. You know, that was how Aristotle, the famous Greek philosopher, approached the world. He essentially said, I have an idea, and since I'm a freaking genius, my idea must be right. Yeah, he never bothered to check out many of his ideas. What a fascinating modern age we live in. Some even consider me one of the first true scientists as a result of my ideas and how I use that evidence. I will only accept ideas if they can be demonstrated in nature. Tycho Brahe's Observatory in Denmark. Oh, to be rich and not have any real responsibility. It's a good thing I inherited all this money from my father, a nobleman who was very close to the Danish court. It allows me time to study the heavens and record their motions using very precise measurements. Let's take a look at today's mail. Bill, sweepstakes, Bill? What's this? A copy of a book? Mysterium Cosmographicum by Johannes Kepler? Let's take a look. The Copernican model of the solar system with the sun at the center instead of the Earth? Ha! Poppycock! Still, I'm impressed with this young man. I think I might sponsor him. I have money falling out of every closet anyway, and since we're both interested in observing the sky, it'll be worth it. After all, I can't spend all of my money on my prosthetic noses. Funny story. So I'll admit I'm a bit of a hothead and I got angry in 1566 with another nobleman and dueled this guy in the dark. He managed to chop off part of my nose. Haha, good times. Anyway, I wear gold or silver noses to look pretty. Pretty awesome, that is. Anyway, let's invite Kepler here so we can discuss things. What's up, Tycho? Can I call you Tycho? Sure, whatever. Hey, let me introduce you to my wife, Kirsten. Don't you steal my husband's data. Seriously, don't steal it. I will rise up with great vengeance and furious anger. Okay, I'm not gonna steal it. And my sister, Sophia. She helped me with a lot of my measurements. Shocked? That's right. Girls can take astronomical observations too. I'm sure history will forget I was involved until much, much later. So, my brother tells me that you have this crazy view that Copernicus had that the sun is at the center of the universe. Are you an idiot or something? Because last I checked, the Earth is awesome, so we must be at the center of it. I mean no disrespect, but I think that by analyzing all these data you've collected, and done nothing with, I can show that the planets follow distinct laws of motion. Knock yourself out. I'm pretty sure you'll find the Earth at the center, just like Europeans have believed for centuries. Well, we have some of the finest equipment here, not available anywhere else in Europe. Great. I'll get to work. Kepler studies over the years. They only gave me part of the data. If I could only get more. Years later, Brahe is at a banquet of another nobleman. Man, I gotta pee really bad, but getting up to go potty would be rude. Oh, I died from internal peeing. You killed my husband, you jerk. He was only 55 and was in nearly perfect health. Nuh-uh. His bladder very clearly burst because he waited too long to pee. You can't pin that on me. Sweet. I've been named Danish Court Imperial Mathematician. Now I have access to all of the data I need to show that there are 3 distinct laws that govern the motion of the planets. Kepler wrote about his 3 laws of planetary motion and changed how we look at astronomy today. Analysis of Tycho Brahe's body centuries later showed high levels of mercury in his hair, suggesting that he could have been poisoned. We do not know this for sure, as many scientists and natural philosophers at the time investigated mercury and even saw it as a curative. The bridge of his nose was also stained green, suggesting that copper was the primary metal used for most of his nose prosthetics, not gold as he had claimed. And done. Thanks, everybody, for listening. So the whole point of the story is to not only recognize that there's a history behind the rules that we learn in class, that these rules develop over time as we gather more and more evidence. A lot of that history can be pretty funny and interesting. And I also think that it's worth noting here that although Johannes Kepler is the person who is largely credited with these laws, it wouldn't have happened had Kirsten Brahe, Tycho Brahe's wife, not collected the data, and it wouldn't have happened had Sophia Brahe, his sister, who was also a data collector but also recorded all of his observations. None of this would have happened. And it's really important in the sciences where we give credit where credit is due. And the unfortunate truth of the matter is that a lot of the time scientists who are women tend to be left out of the stories, and I want to make sure that we have a complete story here in class. Now, there's a handout that you picked up when you walked in that I'd like you to turn to now, and that is asking the question, what did Kepler actually learn, all of the Keplers, and what did the Brahes learn when they were investigating these data? And this is also a good opportunity for us to understand some of the things that we've learned about planetary motion, but I'm going to split these laws up into 3 simple explanations, and then there's also going to be a technical definition there. And so you'll notice here for law number 1, which I call the law of shape, that you do not have on your handout the orbit of a planet around the sun portion of it. And so I would suggest that you write that down. As always, I can't force you to write anything, but you really need to know you as a learner, and if you don't write it down and then struggle a little later on when you're expected to show what you've learned about it, maybe that's an indication that you should write it down. Your call. So law number 1 is the law of shape, and this is a big law that people tend to have a misconception about. largely because it is incorrectly displayed on the internet and in books. We got to be real cautious about this. While it is true that many orbits are close to circular in shape, so Earth's orbit has what we call an eccentricity of 0.97, which basically means that it's 97% of the way to a circle. But some of the outer planets' orbits really show what the Kepler's first law of planetary motion really says, which is that the orbits of planets are oval in shape, even if those ovals are closer to a circle than not. It's a really rare occurrence that we would get a near perfectly circular orbit. So law number one says that the orbit of a planet is an ellipse, which is another way of saying oval, and the sun's center of mass is at one focus. Now, the focus of an oval is not the center of the oval. It is not this point right here on this diagram. There are two foci, that is plural. There's a focus. Well, there's a focus here and there's a focus here, and you'll be responsible for understanding the characteristics of the law. So if you need help to remember what the law of shape, the first law, says about where the sun would be located in an orbit, it's offset. It's either to the left or the right. It could be at either location. And in fact, depending upon whether you're looking at the orbit from above or below, it's really just what direction you're looking at it from. If you need something to help you remember this, think of Stewie. Stewie's head is an oval shape, and one of his eyeballs is at one focus, his other eyeball is at the other focus, and that could help you to remember the shape of an ellipse and where the sun would be located. It is not in the center. I'm telling you right now, there's a test question that will have options of the sun being in the center, and if you select that, that will not be as correct of an answer as if you pinpoint that it is an oval with where the focus is. Second law of planetary motion. Let's go ahead and just take a second to write. Fill in the parts of this that you don't have on your handout. Okay, you got it. Law number 2 is the law of speed. The technical definition, and you don't need to know the technical definition, I'm just putting it up here for students who might be interested in it. The technical definition says a line joining a planet or comet and the sun sweeps out equal areas in equal intervals of time. That is mathematical talk. That's geometry talk. What it really means, and the reason why I call it the law of speed, is that the planet is moving faster in its orbit the closer it is to the sun. And that allows it to go the same distance over a particular perimeter distance over a particular point of time than if it were farther out. And there's a logical reason why a planet moves faster as it gets closer. I'll give you a hint. It has something to do with our discussion of how gravity works. And so based upon what we learned last class about what sort of factors govern gravity, I just want you to think for a second, why would it make sense in terms of gravity that a planet would move faster when it's closer to the sun? What is the pull of gravity like when it's close to the sun as opposed to when it's far away from the sun? Take a second to think about that. In fact, you know what? One thing that we could do here is put your thumb up if you think that the gravity is stronger when the planet is closer to the sun. Put your thumb down if you think the gravity is weaker. Everybody's got to put a thumb up or thumb down. Okay, if you put your thumb up, that's the correct answer. This is an issue of accuracy. A planet would move faster when it's closer to the sun because the pull of gravity is stronger. Thumb up. The third law we call the law of time. Let's spend a second to write some of these things down. Write down whatever you don't have on your handout. So the technical definition for law number 3, the law of time, says that the period of a planet increases rapidly with the radius of its orbit. And in this context, period is referring to time it takes for the planet to make one orbit around the sun. There's a reason why the other period is called period, because it refers to a particular time. So if the period is the time it takes for a planet to make one orbit around the sun, law number 3 basically says that the bigger the orbit is, the longer it's going to take a planet to complete one orbit. And that should make sense to us if you think of a sports example. If you think of running around a track, there's a reason why when you have the choice to run anywhere on a track, you should always run on the inside. And the reason is because the inside of the track is a shorter distance than running the outside of the track. So when you see a race with all the racers lined up, and they don't have to be in particular lanes, they very quickly all move to the center of the track because they don't have to run as great of a distance when they're in the center of a track. And here's some comparisons to this. Let's compare two planets. Let's compare the closest planet to the sun, Mercury, and the farthest planet from the sun, Neptune. And what I have on this table is their distance from the sun in astronomical units. We have not talked about astronomical units yet. 1 astronomical unit is the average distance that Earth is away from the sun. So Earth is at 1.0. Mercury is closer to the sun. Specifically, it is about 4/10 the distance that Earth is away from the sun at about 0.3 AU. It only takes Mercury 88 days to orbit the sun. Every 88 days, every little less than 3 months here on Earth, Mercury orbits the sun once. How long does it take us to orbit the sun? Guest teacher, you can go ahead and pause this and let's ask if there are any students who know the answer to that question. How many days does it take Earth to make one orbit around the sun? Yep, that's right, but if we're going to be specific, it's not just 365. If somebody said 365 and a quarter or 365.25 days, that's the most precise answer. And the reason why that precision matters, this is the reason why we have leap years. Every 4 years we have a leap year, because if we didn't, all those quarter days would mean that when the sun rises and sets on the horizon at a particular time of year would continually get more and more off from where the Earth actually is in its particular orbit. So what we do is we take each of those quarter days every year, 365.25 days, we add them all up, a quarter day plus a quarter day plus a quarter day plus a quarter day, and every 4 years we add a day at the end of February, making it February 29th, so that we have an opportunity to make sure that we keep our sunrise and sunset at appropriate places for the season of Earth's orbit. Neptune, 30.1 astronomical units from the sun. Neptune is 30 times the distance that Earth is away from the sun. And get this, it takes Neptune 165 years to orbit the sun once. All right, let's think about it. The signing of the Declaration of Independence was in 1776, right? So 1776 to 1876 to 1976, plus about 43 years. It's been 243 years since the signing of the Declaration of Independence. Neptune has not quite made 2 full orbits around the sun since the signing of the Declaration of Independence. Space is huge. These things take time. And I know that many of you in the audience are wondering, well, what about Pluto? And why did that evil, evil man, Neil deGrasse Tyson, make Pluto not a planet? Well, the first thing that I want to mention to you is that Neil deGrasse Tyson didn't make Pluto not a planet. He just has been discussing it a lot in public. The change was made by a group of tens of thousands of astronomers who recognized that our definition of a planet didn't make freaking sense. And our definition of a planet didn't do a good job of helping us to understand what Pluto was. And so in the image that you see before you projected on the screen right now, these are how much better our photos of Pluto have gotten over time. And those last few photos right here and here are high-resolution images when the Cassini spacecraft flew past Pluto a couple of years ago. This was the best look at Pluto we've ever had, because when you use a telescope to see objects that are really, really far away, Pluto is approximately 40 astronomical units on average away from the sun. At that distance, it is really hard to get clear pictures with telescopes. So basically, you solve that problem by sending a spacecraft that took a very long time, over a decade, to get to Pluto so that we could actually take images of it, and those images were sent back to Earth. Why isn't Pluto not a planet? What is a planet? A planet is defined with the following four criteria, and this does a much better job of helping us to define a planet. You know, folks, without this definition, I know you love Pluto because it's something that you learned about in elementary school, and I don't know if you all are at the age where maybe you haven't been learning about Pluto as a planet, which would be accurate. But if we don't consider some more refined criteria for what makes a planet, elementary kids would be like needing to know like 30 plus planets in our solar system. We're finding as our technology improves that we are getting so many more objects in our solar system that fit the criteria for a planet. So if we don't nail it down, we're recognizing that our current conception of what defines a planet, the 8 planets in our solar system, could balloon up to dozens or even 100 plus objects. So a planet must orbit the sun, duh. Okay, so anything that doesn't orbit the sun directly would not be considered a planet. This eliminates moons as contention for being a planetary object. It can't be the moon of an existing planet. It has to be massive enough that its own gravity keeps it round. This eliminates the asteroids in the asteroid belt from being considered planets. Otherwise, we would have millions of planets in our solar system. And then our fourth criterion, this is where Pluto really struggles with it. It has to be big enough to dominate its orbit. You may not have heard that Pluto's orbit actually crosses Neptune's orbit. Pluto also has 2 moons that are very close in size to Pluto itself. Pluto does not dominate its orbit. And so in that regard, from a scientific standpoint, science is always changing, folks. Like we said at the beginning of the year, science does not tell you absolute truth. Science is not about right or wrong. It is about getting the best picture of things according to the evidence, and the evidence doesn't support Pluto being a planet. Now, if you have emotions about that, that's okay. I'm never going to tell you how to feel. But the reality is that in science, we define things according to evidence, not how people feel about things. We certainly consider how people feel about things, which is why I'm taking the time to try to help you to understand what a planet is. If I didn't care what your feelings were, we wouldn't even be talking about this. But since I do care about your feelings, I just want you to know that this is why science defines it as not a planet. Okay, so hopefully at this point, I haven't quite been checking the time, but I'm guessing that we're probably close to break. And if there's any time left in class, you can just relax until the bell rings. The sub is the ultimate, our guest teacher is the ultimate determiner as to whether or not you actually get a break. And so if you were attentive and you were paying attention to the slideshow and writing down notes were appropriate, or at least had your eye on the screen, you get to take a break. If you were not participating, you don't get to take a break. Okay, that's how these things work. You got to earn the privileges that you get in class. It's always been that way. It's always going to be that way. So, I just want you to be prepared and get the things that you want. If you want these things, this is what you got to do in order for it to happen. And so, guest teacher, you can go ahead and pause the video, and then we will start this video back up when you return from the exercise out on the baseball field during the second half of class. Okay, everybody, welcome back. I now need to do a little switch over here because let's talk about the sort of ideas that we were exploring with that piñata out on the baseball field. The idea behind the piñata exercise is just to get you thinking about, in the early formation of our solar system, what sort of objects were there and what sort of evidence have we gathered that supports the idea of a large object named that we've named Theia striking the Earth at a time in the distant past and knocking out a huge chunk of the surface and the mantle of the Earth, and that resulting in the formation of the moon. Like, how do we know that that is the best hypothesis of what happened? Now, the model out on the baseball field is not a perfect model. The idea behind it is that we're modeling the Earth, represented by the piñata, and Theia, represented by the softball, striking the Earth. And if this model were perfect, what I would want to happen is the softball would strike the piñata, the candy would fly out of the piñata, and then we would see that candy coming together and orbiting around the piñata. Now, obviously, that isn't going to happen. So this is not a perfect model, but if we can if that helps us to imagine what happened by thinking about the piñata example, and comparing that to what the evidence suggests, that's what we're trying to go for here. And so the big thing that I need to emphasize here is that the best evidence that we have collected for how the moon formed came from us traveling to the moon and bringing rocks back home. You can actually touch moon rocks at several museums, like rocks that have been brought back from the moon. You can touch a moon rock at the museum at the Johnson Space Center in Houston. You can touch a moon rock in Huntsville, Alabama, where the U.S. Space and Rocket Center is. You can touch a moon rock at the Smithsonian Institute, the Air and Space Museum in Washington, D.C. And it's a really cool experience to touch what you think, what we know was a rock that was present on the moon. This is a picture of the Apollo 17 mission, which was a really important mission because this was the mission that Jack Schmitt was an astronaut on, and Jack Schmitt was the first geologist astronaut. Remember, a geologist is someone who studies the Earth and Earth's structure, and we needed to send a geologist to the moon because that geologist is best poised to interpret the evidence that they're gathering while we are on the moon. And before we landed on the moon, we had all sorts of hypotheses, educated guesses as to why the moon formed. And most importantly, why does the Earth have a moon that is much, much closer to its planet size than any other moon in our solar system? Earth has a huge moon compared to its size. No other planet in our solar system have moons that are as close of a size, at least in the inner planets. But I'm pretty sure that that's true of all 8 planets, okay? None of the 8 planets other than Earth has a moon that is as close in size to its diameter as Earth. And so what did we think beforehand? Well, here's sort of how the data collection has worked out on this. This is all combining together to help us to understand what different bodies out in space are made of. From 1969 to 1972, we had the Apollo missions, which all collected moon rocks. On the first mission, the very most famous mission, hugely famous in human history, the Apollo 11 mission, we left a range reflector on the moon, which is basically a very sensitive mirror, and we left a seismic sensor on the moon, sort of like what is used to detect earthquakes here on Earth, and we have been continually collecting data from the moon. We know that we've been to the moon, folks, because we can detect that range reflector and get laser reflections off of that range reflector. Okay, it's not a conspiracy. There's direct evidence that we can collect that shows that there are objects that we placed on the moon. And so we're continually collecting data from those instruments that we left back in Apollo 11. Apollo 17, we went to a different part of the moon to get different rocks for comparison. And then there's been a series of missions that, of course, all collected rock samples from Mars. The Pathfinder mission, Spirit, Opportunity, and most recently Curiosity. We have a helicopter that is going to be going to Mars soon. It's basically a drone that when it unfolds, there's a helicopter. And you know what? In our next large group, I might see if I have time to show you the video of the Mars helicopter because it's a really cool piece of technology that will be cool for you to see. And then the Rosetta missions from 2014 to 2016 orbited a comet and then deliberately crashed into that comet, and we studied the rocks that were ejected out into space by using reflective science, by analyzing the light off of them. And when we put all those things together, we get a very clearer picture of how our solar system formed. The 4 hypotheses for moon formation, and I don't know how much time we have here, so I'm just going to go through these really rapidly. The capture hypothesis suggested that Earth's gravity captured an already formed moon. We have some evidence that this doesn't make sense. We studied the oxygen isotopes, the radioactive isotopes of the moon and the Earth, and they share common features, and so it does not make sense that the moon came from somewhere else. The moon is basically just too much like Earth to support this hypothesis. The co-accretion or condensation hypothesis is basically the hypothesis that the moon and the Earth formed at the same time. And if this were the case, it's much more likely that the moon would have been part of Earth rather than having been its own natural satellite. Also, the moon's iron core is way too tiny to have formed from the same collection of elements. Next, the fission hypothesis that the moon split from Earth. This is probably the oldest hypothesis, and it is the one that has the least grounding in science. The idea behind this that if the moon was, or if the Earth were spinning fast enough early in its formation, that part of the Earth would spin out into space. But our understanding of how gravity works really does not. The math just doesn't work out. It's not even close. The moon isn't orbiting the Earth following the equatorial plane, which we would expect that if it spun out into space. And the Earth would have been spinning so fast under those circumstances that it really would have just shaken its entire self apart if that were the case. When we went to the moon, the best supported hypothesis became the giant impact hypothesis, and we've upgraded it to a theory because we now have a really good collection of evidence. Folks, a theory in science is not just an idea. Okay? A theory is understanding based upon evidence of a really clear picture of how something works. When we say that evolution is a theory, we mean that there's a lot of evidence backing it up. When we say that the giant impact theory is a theory, we say there's a lot of evidence backing up. Gravity is a law, an even stronger suggestion, because it basically works the same way under all circumstances. So, the prevailing hypothesis is that an object the size and mass of Mars collided with Earth. This object, we call it Theia, a protoplanet. And when they collided, a chunk of Earth was likely knocked out into space and came together and formed our moon. We have lots of evidence, especially from what we collected on the moon, to support this. One, Earth's rapid spin would result from a collision with a large object, so that's likely why we have a rotation every 24 hours for the Earth. Analysis of radioactive materials in both objects is the same, indicating that they have shared elements in the past. Debris patterns from other parts of our solar system suggest that this makes the most sense. And when you analyze early magma oceans on the moon from the rocks, there is evidence that those rocks formed under a really high energy collision. In other words, it wasn't just an object floating out in space that was brought together by gravity. It was something that ran into something else. So I hope I did this within time. I hope you have a great day, everybody. At this point, you can have free time for the rest of the mod. And thanks for watching, and I will see you when I return in large group on Friday.